Hey, we're back with factoring again. We're factoring, this time we're doing difference of two squares, or as I like to call it, dots. Difference of two squares, dots. Love it. So, yes, we're going to be learning to factor these, okay? So let me write some problems up there. I forgot to do that. All right, so I got my example up here. And just like how I did with the GCF video, I'm going to kind of show you it's the reversal of another process, okay? And that would be this right here. So dots, difference of two squares, it's a very particular type of polynomial, okay? And I'm going to talk about that in a little bit, but let's just review this first, okay? So you might remember from before, we've reviewed FOIL already, first, outer, inner, last. That's my order that I would multiply these two binomials, okay? So I'll do the first term times the first term. So x times x, x squared, okay? X times negative 1y. So that would be negative, I would just kind of lump them together, negative xy. This one, y times x, okay, and that's positive, so it would be plus, you could write yx, but I usually do it alphabetical order, xy, okay. And then positive 1y times negative 1y would be negative 1y squared, okay. And then again, like all FOIL problems, you're going to, not all, but usually you're going to be left with two terms in the middle here that are like terms that you can combine, okay? And so xy, so negative 1xy plus 1xy. So negative 1 plus 1, these guys cancel each other out, okay? So x squared minus y squared is what I am left with. So that is how I would FOIL that, okay? Now how does that relate to this, okay? You might notice this is the answer to that. So when I'm asked to factor a difference of two squares binomial, I would end up with a very simple answer, okay? And it doesn't require me to do much work at all, okay? But the big thing is that you identify, is it a difference of two squares binomial? And what is it? Difference of two squares. Let's just break that down. Difference is that math word that means subtraction. So it's two terms, and that's the two terms that are being subtracted, okay? So that's difference of two. And then squares, okay? We're not talking the shape, we're talking perfect squares. What is a perfect square? A perfect square would be a term that you could do something times itself to get that, right? So 64, I would say, is a perfect square because 8 times 8 is 64, okay? 121 is a perfect square because it is 11 times 11. X squared and y squared are perfect squares because x squared, you could write that as something times itself, right? X squared you could say as x times itself, right? X times x. And then y squared, also a perfect square because you could say y times y, right? So that's the key, is that it's two terms being subtracted, and those two terms are both perfect squares. Both of them are perfect squares. So when you see that it is two perfect squares being subtracted from each other, you can factor it in a very easy way, okay? And this is actually step one, is what I would tell my kids. Step one is to break up your polynomial like this. Kind of take the square root of it, or ask yourself, okay, x squared, what times itself equals x squared? And obviously it'd be x. And the same with y. So you kind of break down your two terms into what times itself equals that. And then step two is just very easily breaking it up into these two groups. Okay, again, I said it's the reversal of this. Okay, so there's a pattern here. Okay, within a dots factoring, it's always going to end up as one of the groups is a plus and one of the groups is a minus. You notice that this example had that, right? One is a plus, one's a minus. Okay, and then to fill in these blanks, you just take one, right? You just take whatever the square root of that term is and fill that in here. So it'd be x plus y. So it's one from each of these. So x plus y and then x minus y. Okay? And that's it. That's the answer, right? So dots is the easiest way of factoring, but you can only do it with a very particular group of binomials. Okay? That is how you factor it. Okay? And it doesn't require any other work than that. Okay? Which is great. Because again, when you would FOIL this, the reason you might be saying, okay, why do you need the plus and the minus? Okay, that's actually key because, right, the fact that this was a plus and a minus here, okay, that is what made these two middle terms cancel each other out, right? Because this was x times negative y, that gave me a negative xy. This was positive y times x, which gave me positive. So the fact that these were both, right, that these were different signs, okay, made these middle terms cancel out. So I'm just left with the x times x and then the y times negative 1y there. So again, the reversal of that is it's very easy to do, okay? But you just have to recognize when it's two perfect squares, okay? Let's do a few more examples and then hopefully you got it by then. We're back and we're going to play a little game here called Is It Dots? I know that's not probably right grammar, but that's okay. We're just going to look at these four binomials that I put up here, and we're going to answer. Would this be able to be factored with a with the dot strategy, right? And so again, let's break these down. 4x squared minus 49, okay? So again, for this to be dots and able to be factored in that very easy way, I need to determine, are these two terms perfect squares? Okay. And so 4x squared, okay, again, for it to be dots, I would need to say, okay, that is a term times itself would equal that, right? So 4x squared, well, the 4, right? 4 is a perfect square because you can say 2 times 2 is 4. And the x squared, we said that in the last one, x squared is a perfect square, right? Because it's x times x. So kind of putting those together, wouldn't 2x times 2x equal 4x squared? Absolutely. Okay, so that is a perfect square. So we're good there. Next check, is it subtraction? Yes, it is. Great. So that fits because it only can be subtraction. Then 49, is 49 a perfect square? Yes, because 7 times 7 equals that. Okay, so yes, this is dots. And so I could factor that into, again, following the same pattern, 2x plus 7 and then 2x minus 7, right? One with a plus, one with a minus, taking one from each of these groups in there. There we go. Number 2 is number 2 dots. Well, let's do our check. X squared, that's a perfect square, x times x. 16, that's a perfect square, 4 times 4 is 16, but it is not a difference. It is not subtraction, right? You see the plus here. It has to be subtraction. So we would say no. And we would not be able to factor this, okay? Because not only is it not dots, but it also doesn't have any common factors. So nothing to do there, okay? Not dots. Number 3, x to the 4th minus y to the 4th, okay? This one's subtraction, so we're good there. Is it 2 squares? Well, x to the 4th, again, that's a higher exponent, but could I say, is that something times itself? Okay, x to the 4th, x squared times x squared. You see that? X squared times x squared would give me x to the 4th. And that is, in fact, something times itself. Okay? And then y to the 4th would be y squared times y squared. Okay? So, yes, those are perfect squares. And something fun's going to happen here. Get ready. So this is, I would write x squared plus y squared, and then x squared minus y squared. But hey, check this out, okay? Double dots, double dots. Because look, x squared plus y squared. So that I can't do anything with that because it's not subtraction. Even though these two are perfect squares, I can't do that. But look at this guy. X squared minus y squared. Still two perfect squares and subtraction. So what do you know? I could just take this guy and dots, factor that with dots, right? So I could say this, just the second group is x plus y, x minus y. And then again, my first group can't be factored, so I could just write that out here. How about that? So that would be the full answer to this, would be x squared plus y squared, and x plus y, x minus y. Wow. Okay, number 4. Number 4. 25x squared minus 50. Okay, tricky one. 25x squared. Is that a perfect square? Yes, it is. 5x times 5x. 5 times 5 is 25. X times x squared. Passes the test. That's a perfect square. Subtraction. Yes. Good. 50. Uh-oh. 50. What times itself equals 50? Well, 10 times 5, but that's not something times itself, right? 25 times 2, that's not something times itself. So, no, this could not be factored with dots, but you might recognize if you watch my GCF video, how could this be factored? We could factor it with GCF, right? This has a GCF. And so if I think about, okay, what's the GCF of 25x squared and 50, right? Well, I listed as 50. One of the things that multiplies to get 50 is 25 times 2. And obviously 25 has 25 times 1. So these both have 25 as a factor. That would definitely be the greatest common factor. And I would not include an x in here because this 50 doesn't have an x with it, right? So if I factored this with GCF, I could get 25 on the outside, and then 25x squared divided by 25, 25s would cancel, and I would just be left with x squared. And then 50 divided by 25, or negative 50 divided by 25, I can say negative 2. Okay. So even though it can't be factored with dots, we can still factor just using another strategy. Okay. So that's kind of getting into what we're going to be dealing with, the difficulty of this. Okay. Like the first two, the strategies themselves aren't super difficult, but it's just as tough sometimes to recognize which strategy do you use in which situation. Okay. And so that's what I'm going to try to work on with you here. Okay. So that's all, I think. I was going to do some more examples, but I figured we're good. I'm going to do some more dots in another video, I think, but for now we're okay. Thanks for following. Bye.